Swayam Prabha. Digital India. Educated India.
Okay, so you see, I'm just continuing with my earlier talk, which was about trying to do trigonometry on a curved surface. Okay, and so you see to quickly tell you what we saw there is that the usual trigonometry, which is of course usual means plane trigonometry, that deals with triangles on the plane, and then the important variables are the sides of the triangle, which mean the lengths of the sides of the triangle, and the three angles, the interior angles of the triangle. Okay, and a lot of stuff about that. You've been studying that from probably 7th standard or 8th standard at least. You have studied similarity, and then you have studied congruence. Okay. And strong congruence is very strong, similarity is weaker. All right, and the difference being the difference in both being that in the case of congruence, the sides must be the same length, corresponding sides, whereas in similarity they will be proportional. But in both cases, what is common is that the angles are the same, corresponding angles are the same. Okay, so you think of similarity as some kind of magnification. Okay, and and then the standard trigonometry that you learn is that the sum of the three angles of a triangle is 180, and I'm going to use radian measure so that I can use I can relate the arc length to the angle that the arc subtends at the center of a circle. Okay, so I use radian measure, and pi radians is same as 180 degrees. This is the same as 180 degrees. Okay. The sum of the three internal angles of a triangle is 180 degrees. That's something that you know. Then there is a famous sine rule which says that the sines of the angles are proportional to the lengths of the sides opposite to those angles, right? That's the sine rule. Okay, and then you have the cosine rule. The cosine rule is it is a generalization of Pythagoras. The Pythagoras theorem, which says that if you have a right angle triangle with hypotenuse A and the other two sides B and C, then A squared is B squared plus C squared. But then if the angle is not a right angle and you have some angle alpha, then there is a defect, and that defect is minus 2 BC cos alpha. All right, so this is the cosine rule, right? So this is the usual trigonometry. All right, so the point is that now so I raised two crazy questions, namely instead of taking a usual triangle made by straight line segments on the plane, you replace it with a triangle made by curves. Okay, so it's funny, it's a triangle. Why would you call such a thing a triangle? Well, that's our definition if you want. Basically, there are again three vertices. So you have this vertex A hat. This is another vertex B hat, and this is the third vertex C hat. And the point is that you see there are these curves that that connect these three vertices. So there is this curve. So let me change the color. So here is one curve, and this curve is kind of connecting B and C, right? And the length of that curve is A. Okay, and of course you're assuming that this is a nice smooth curve and that you can calculate its length. Okay, so you must understand that these are all things that are being said geometrically, but there's a lot of math behind it. Okay, so for example, there are curves. I have to take a moment to tell you that there's a lot of deep mathematics in very buried here. So you see, what I mean by a smooth curve is a curve smooth in the sense that if you take any point, you can draw a tangent at that point. There's a unique tangent at every point, And as you move the point, the tangent also moves smoothly. Okay. So that means the tangent is continuous. All right. And if you take a curve which has a kink somewhere, a sharp point, then you see that at that point, if you approach the curve from two different directions, you get two different tangent directions. And then that kind of a curve is not smooth. At that point, that's a sharp point. So it is physically also sharp, and mathematically also it is, it's not smooth. Okay. So, why this is so important is because when you see, all this is said geometrically, but when you want to write it down mathematically, so that's what mathematics is all about. You need to bring in the mathematical, a theory that is required for that. So you have to make some definitions. So the question is, how do you put all this into a mathematical definition? Okay, so that is what makes up calculus. All right. So for example, basically a continuous curve would be, if you want a continuous map from a closed interval on the real line, which starts at the point, let us say this vertex b hat, and goes all the way up to c hat, and this is supposed to, by the continuity of the map, it's supposed to trace a continuous curve. Okay. Now you can have a continuous curve which can be very jagged, which means that it need not be smooth. Okay. So I can draw something very jagged, and that's not a smooth thing. So if you want it to be smooth, then you need to also have that this curve has a unique tangent at every point. And that means that this function that is defining this curve from a closed interval on the real line, which you can take, for example, you can take the closed interval 0, 1, that function should be not only be continuous, it should also be differentiable. All right. Then that will ensure that at every point you can draw a tangent. But just because you can draw a tangent at every point doesn't mean that the tangent moves continuously. So the tangent, the existence of the tangent is the existence of the derivative of that function. That the tangent moves continuously as you move the point on the curve is the condition that that derivative is continuous. Okay, so these curves are given a special name. They are called C1 curves. C1 means first continuously differentiable. That means they're differentiable ones, and the derivative is also continuous. Okay, and then there's a whole hierarchy. There are continuous. So what really happens is there are all kinds of crazy things. There are continuous curves which are nowhere differentiable. There are continuous curves which are nowhere differentiable. Then there are continuous curves which are differentiable, but the derivative is not continuous. Then there are continuous curves which are differentiable and the derivative is continuous, but the second derivative does not exist. Okay, then you can imagine the second derivative will exist, but it is not continuous. Then the next one is the second derivative exists and it's continuous, and then you can go on to the third derivative. So you see, you get a whole hierarchy of families of curves. Okay, so and all of this is very very important, because there are certain as I told you, it's mind-boggling. There are curves which are nowhere differentiable. There are continuous curves which are nowhere differentiable. That means you give me 2 points on the plane, I can join it by a curve. Okay, the curve is continuous, meaning that if you trace it, there won't be any break in that, if you want, in a very intuitive sense. But here's the catch: you cannot trace it. Okay, why you cannot trace it is because if you do it with your hand, you see, if you want to trace a curve, your hand movement has to be such that the tangent moves continuously. Okay, when I don't have any tangent at any point or at some point, from that point, how do I go to the nearby point? I don't have any direction. So I don't have any way of tracing that. So you must understand something. When we geometrically trace something, okay, the curve has to be at least piecewise smooth. I can draw something like this, then artificially make a break here and put a kink like that. But any continuous movement that I make will always produce a curve which is continuously differentiable. But you can break at several points. So what you get is what is called as a piecewise continuously differentiable curve, or it's called a piecewise smooth curve. Okay, so there are curves Curves, if you just say a curve is continuous, it's a very, very deep and very, very, it's very deep because you see the definition is so, as less demanding as it can be. You're just asking for continuity. You're not asking for even differentiability. So there are, will you believe it, there are curves which are continuous but nowhere differentiable. All right. And what does it mean? It means you can't draw them. You cannot draw them. All right. No machine can draw them. Okay. You can only make a scatter plot. Okay. And these belong to a different dimension of things. They are fractal curves. For example, fractal curves are like that. I don't know. I saw that in one of these lectures, somebody is going to talk about fractals. I don't know whether they did or maybe I'm not sure. So there are these curves called fractal curves, and it's very funny. There are fractal curves. The beautiful thing about these curves is they are continuous. You can join 2 points by a fractal curve. Now, what is the strange thing is that you take any point on that curve, you cannot draw a tangent to it. At no point on that curve can you draw a tangent. That means it's, what's happening. If you take a nice smooth curve, take a curve which is, let's say, differentiable, where there is a tangent at a point. If you zoom it close to that point, it almost looks like a straight line. And that's your tangent if you want. All right, that tells you what the tangent is. But what happens in fractal curves is that, you take this point and then you zoom it, it's still jagged. See, the point is that it's jagged. You try to zoom into a point, it's as jagged as it was before. So there's a recursive thing. That's what the fractal is all about. That you zoom it and it still looks as jagged as it was forever. And it happens like that forever, no matter how close you go to the point. So you cannot draw a tangent. So these kind of curves, you cannot draw them. But here's the amazing thing. You can have a square where the edges are all fractal curves. Okay. What is the strange thing about these, fractal curves? They at no point, it looks like a square. So it's not exactly straight line segments, because straight line segments, that you can draw them. You can have something like very close to that. The point is that, and another thing about these fractal curves is, you take any 2 points on the curve, nearby points, okay? Physically, they are nearby, okay? But if you calculate the length of the curve from this point to that point, it will be infinite, okay? It's absolutely crazy. That's because it's just getting jagged. The length is infinite. Okay, so these are curves with infinite length between any 2 points of the curve. But still, the crazy thing is they can enclose a finite area. Okay, so you must understand that when you say a curve is just continuous, it can be absolutely crazy. And these are all things that we study in, as pathologies in analysis or in topology. For example, in topology, there are these curves called space filling curves. Now, these are just curves which will fill space. Okay. You must understand the significance of this. See, the point is that a curve is one-dimensional. If you take the plane, it's two-dimensional. Usually, you cannot fill a two-dimensional object with a one-dimensional object. It should not be possible. All right. But the nice thing is that, you can really do this by, you can use curves, continuous functions defined on a closed interval on the real line, say 0, 1. And you can fill up not only the plane, you can fill up n-dimensional space. These are called space filling curves. So if you just say a curve is continuous, it can be pretty complicated, okay? It can be some highly pathological object, all right? So you must understand that when I am talking here, I am talking about decent curves which are C1 continuous. That means, the function that defines the curve is continuous, it's differentiable, and the derivative is also continuous, okay? And there's something very nice. When you take such curves, then the length of the curve between any 2 points is always finite. You can really measure the length, and there's no problem with that. So these curves have a length, finite length, okay? And you see, that is what is being used here. So you must understand that, there's a lot of math here, okay? But you must see that on the one hand, the real math is in assuming that the curve is continuously differentiable. that ensures that there is a well-defined length. Okay, and that length is what I'm going to call as A. So it's the curved length if you want. All right. So similarly, now I have three. So I have, this is from B to C, and then from A to C I have this curve. Its length is capital B, and from from A hat to C hat, and then from A hat to B hat there's another curve whose length is C. All right. So you have these three lengths. And what about the angles? You can make the angles as the angles between the curves at the 3 points. And the angle between two curves at a point is defined to be the angle between the tangents. All right. Now again, the question is, for this kind of really curvy triangle, is there a trigonometry? What is the sum of the angles of the triangle? Pi. No, you must understand that it can be made into anything. Okay. Because I can just draw it whichever way I want, right? You can just have, you can have it, you can also make it 0. And the maximum I think you can make is, it looks like you can make it 6 pi, right? Because you see, just imagine, I can draw something like this, right? See, if I can just take 3 points, okay? And then, I can take just lines like this, let us say, and then, you do, something like this. You can imagine drawing a curve like this. The sum of 3 angles is 0. Because at each of these points, you see there's one tangent. The angle between the tangents is 0. This is a curve for which the sum of the 3 internal angles is 0. Okay, I can do this. All right, and then I can do something else. So let me write this: alpha plus beta plus gamma is 0. So alpha equal to beta equal to gamma is 0. This is possible. Then I can, of course, I can do this other thing, namely, I can take these 3 points and take these 3 lines like this, and then I can do this, namely, and so let me draw it very carefully. Oops. I'm purposely drawing it in such a way that this angle is now 2 pi. All right. So here also it's 2 pi, and here, and so is it here. And here alpha plus beta plus gamma is 6 pi. I can do this also. This is also allowed. This is also a triangle. Okay. Right. So moral of the story is, it can be literally anything. But the point is is it just arbitrary? You can understand that the way this is got to do something with the way these edges, these sides are turning, right? You can intuitively see that the curvature of these sides, okay, they are going to have an effect on this. So you must expect that the sum of the 3 angles of the triangle can be anything, okay, but it has to be connected to the curvature of the curves, okay, because I need to curve the curves the way I want to get this picture, all right. So you must understand that if you want to really get an answer that I take to this question, that if I take a curved triangle on a plane and take the sum of the 3 angles, that must be related to the curvature of the 3 curves, right? And that should be the trigonometry, okay? And that leads to what is called as differential geometry, all right? So this is for curved triangles on the plane. And then I told you that let's have a more crazy question. Instead of just drawing a curved triangle on a plane, which is a flat surface, now you take a smooth curved surface. You take a smooth curved surface, okay, a smooth wavy curved surface, all right, and then on that you take 3 points, A hat, B hat, C hat. Draw a curve, draw 3 curves on that smooth surface. Again, you can make sense of the 3 angles of a triangle and 3 sides. And again, can you do trigonometry with that curved triangle? Now it's a curved triangle on a curved surface, okay, which is more complicated than a curved triangle on the plane, right? And you want to do trigonometry with this, okay? And as you can see, this is the craziest kind of question that you can ask. And the question is there an answer to the sum? What is the sum of the three angles? And I already, indicated to you, intuitively it must be what? It must be, it has got to do with the curvature of the sides. So you need to understand these things. How do you, if you take a curved line, so a curved line means, it's kind of, what do you call it in English? Oxymoron, or, two words, oxymoron, right? A curved line or curvilinear is kind of oxymoronish, but the point is it's what it means is actually curve. So you take a curve and then try to understand its curvature. That's very, very important. How do you understand curvature of a curve on the plane? That's a question that this raises. That's for the question for trying to understand trigonometry for a curved triangle on the plane. On the other hand, if I look at trigonometry for a curved triangle on a curved surface, then I need to understand what is the definition of, what do you mean by curvature of a curve on a surface? Okay. So you must understand that this is slightly more complicated, because you see, when you say, in the first case, it was a curve on the plane, so it's a curve lying on the plane, and you wanted to know what the curvature is. Now the second case, it's a curve on a curved surface. This curved surface is living in 3 dimensions, and there is a curve sitting on the surface. But if you forget the surface, it's a space curve, okay? A space curve can be very complicated, very different from a plane curve. For example, helices, which you come across when you look at the structure of the DNA in biology. Helices are a spring-like, things that you look at. These are all space curves which are not plane curves. You cannot put them on a plane. Okay, they are 3-dimensional. You cannot put them on a plane. And you have to understand the curvature of such things. So you have to understand what is meant by a curvature of a plane curve. You have to understand what is meant by curvature of a space curve. And on top of that, you need to understand what is meant by curvature of a space curve sitting on a curved surface. Okay. So these are the kind of questions that you need to answer, or you should build a theory around these things. And then you can guess that you will get the answer to this question. All right. So that is the direction in which I'm going. So so I told you that if you so the thing is that we want to leave the for the moment you leave the case when you are looking at a curved triangle on the plane. All right, the plane is something that's very familiar. Okay, physically it's flat; it's not curved at all. The next curved thing that you can think of is a sphere. The nice thing about a sphere is that it is curved, but it is curved in the same way at every point. Okay, all the points of the sphere, they are curved in the same way. All right. That's very different from, for example, an ellipsoid. If you take an ellipsoid, all right, take an ellipse and rotate it about its, let's say, major axis, you get an ellipsoid. And then you know that there are portions of this solid oval kind of thing. In the middle, it's more flatter, and it's more curved at the edges. So you see, it's not uniformly curved. All right. But of course, if the ellipse is a circle, in which case the major axis is equal to the minor axis, you get a sphere, and the sphere is uniformly curved. So what you should think of is, let's try to understand what happens to trigonometry on a sphere. And that's what I want to talk about today. All right. Can you draw some inspiration from trigonometry on the sphere? All right. Or is there a trigonometry on the sphere? And the answer is yes, it's called spherical trigonometry. So I told you the nice thing about spherical trigonometry is that you'd start trying to look at triangles drawn on the sphere, all right, and then you want to do trigonometry with that, okay. Now, but the point is that whenever you do something, if you do it too arbitrarily, you will not get anything. The point is that you should know what to relax and try to hunt for, whether that's going to give you something. So look at, so you always derive inspiration from what you already know. In the plane, when you do trigonometry using a triangle, you take 3 points and you join them by these line segments, and then you do your trigonometry. So it's these line segments. What is the special purpose of these line segments? They are the shortest distance. They are the paths of shortest distance. Okay. Any 2 points in space, the shortest distance in Euclidean space, n-dimensional space, the shortest distance is the straight line distance. Okay. And that's why you join them by straight lines. Okay. So basically, how do you make an ordinary plane triangle? You join the 3 points by the curves of shortest distance, which turn out to be the straight line segments. Now mimic that. Now take a sphere and take, so this is the sphere here, and then I take these 3 points A hat and then B hat and then C hat, okay, and I draw a triangle. I have to draw a triangle, and I have to draw a triangle. Of course, I can't draw straight lines, because if I draw straight lines, you know, if you take 2 points on the sphere and draw a straight line, it'll go inside the sphere. It'll not lie on the sphere. I want everything to be happening on the surface of the sphere. All right. Okay. If I draw straight line segments, then I'll be only doing the usual plane trigonometry on the unique plane that contains those 3 points, and there is no relevance to this sphere at all. Right. So I shouldn't do that. I want to see what happens. How the curvature of the sphere is going to influence my trigonometry. So what I have to do is, I take this, for example, if I take this point A hat and I take this point B hat, I have to join them by a curve and now draw inspiration from what happened in the plane case. It should be a curve of shortest length. All right. And what are the curves of shortest length on a sphere? They are the arcs of the great circles joining those 2 points. So you take this great circle joining A hat and B hat. How do you get that? That is O, which is the center of the sphere, and then there is this plane. This plane which contains OA hat and B hat, there is a particular plane. That plane cuts the sphere into 2 hemispheres, and you get a great circle. So you see, the great circle is going to be like this, you know. So it's going to go on like this. So this is a great circle, right? Passing through A and B, all right, which is given by this green line. I mean, so you know, and there is this, and you know, this green line is actually an equator. It's the unique equator which contains the points A hat and B hat. And what do I mean by an equator? It's a circle on the sphere that divides it into 2 hemispheres. All right. So now you see, I have this portion. Which is the shortest distance. Okay, the shorter arc. Of course, if A hat and B hat are, you know, antipodal points, as they are called, the endpoints of a diameter, then this will be both of these arcs will be of the same length. They will be half the perimeter of the circle. All right. So I'm taking this. So I'm taking this. I'm taking this curve from A hat to B hat to be the shorter arc of the great circle, the unique great circle that passes through A hat and B hat, right? That's unique. And these paths of shortest length on a geometric object, they are called geodesics. So there is this word called geodesics. Okay, and so the point is, therefore, if you did trigonometry on the plane, by taking 3 points and joining them by line segments which are points of, which are line segments which are geodesics, they are, you know, curves of shortest length which turn out to be straight line segments in the plane. And you want to mimic that on a sphere. You have to take 3 points on the sphere and join them by great arcs, shorter lengths, great arcs of shorter length connecting those 3 points, and you get what is called a spherical triangle. So this is what is a spherical geodesic triangle. Right. So the analog of an ordinary triangle, the plane, on the sphere is a spherical geodesic triangle. Okay, and then now everything is fine. So you see, from A hat to B hat, I have this green thing, which is the, this is the arc of the shorter arc of the great circle passing through A hat and B hat, and then I can do this like, go on like this, and then from B hat to C hat again I have, well, this is not showing up so nicely, oops. Let me use some other color. Yeah, so from B hat to C hat, I'll put this thing in pink. This is going to be, the shorter arc of the great circle passing through B hat and C hat, all right? And then similarly from, if you want from, let me use some other color, violet, let us say. And from A hat to C hat, I have this purple thing, okay? And that is the shorter arc of the great circle passing through A hat and C hat. Okay. Now this curved thing, which looks like, you take a melon and you cut out a chunk out of that triangular chunk. It looks like that. All right. That is your spherical triangle. All right. And then once you have this spherical triangle, well, everything is nice. Now you have the three angles, namely you have alpha here. The alpha is the angle at the vertex A hat, okay? And of course this A hat is a notation that I am using, but don't get confused. Here the hat doesn't, mean unit vector. Usually hat is put on something to show it's a unit vector. I just want to call it A hat, and I don't want to call it as A, because A is going to be the length of the, the geodesic opposite to that, which is going to connect B hat and C hat, okay? I want to distinguish between this A, which is the length of this, okay, and this vertex, which is A hat. And of course, I'm going to call this angle as alpha. I'm not going to call it as angle A. I'm not going to call it as angle A as you would do, all right, for another reason, because angle A will now have a different meaning. And what is that meaning? It's obvious. You see, you have this, remember that there is this, what is this capital A? This capital A is it is the length of this pink, this pink thing almost looks, unfortunately it looks, very straight, but let me get rid of it and make it look a little curly. So originally I think it was like this, okay? And then, this A is actually this length. It is this, this is the length of this arc of this great circle passing through C hat and B hat, all right? And now watch, I've joined O to B hat, I also join O to C hat, all right? And you see, I am taking a sphere of radius 1, all right? So now you see, this arc length is actually A, all right? Then it's clear that this angle is also A. Because, arc length is radius times the angle, if you measure the angle in radians. The radius is 1, so the arc length is the same as the angle that the arc subtends at the center, all right? So you must understand that there is a small, there's a little bit of a complication. Capital A refers not only to the arc length of this smaller arc of the greater circle that joins B hat and C hat, but A is also the angle subtended by that arc at the center of the sphere, right? So you see, this is A, and then now this is A, then this is C, okay, subtended by this C here, which is the arc connecting A hat and B hat, arc of great circle, smaller arc of the great circle passing through A hat and B hat, and then of course, if I mark it, this is going to be your B, which is the angle subtended by this B, which is the arc length of this great arc in purple that's connecting A hat and C hat, right? So you see, you must understand that the situation is that this A hat is a vertex, alpha is the angle at that vertex, okay, in the spherical triangle, and then opposite to that you have capital A, which is the opposite side, which is arc length, and that capital A is also the angle subtended by that arc at the center of the sphere, okay? So this is what you should keep in your mind, all right? So this is the setup, all right? And then what happens? So here is, so what happens to the trigonometry? So the trigonometry is the following, that you see in ordinary, in the plane you will get the sine rule, sine of the angle by the length of the opposite side opposite to it. They are all in the ratios are all the same. So this is the usual sine rule. And guess what? Here what will happen is that you will have the same kind of thing, but instead of getting A, B, C in the denominators, you get sine A, sine B and sine C. So you are getting sines of the, what you are saying is that the sines of the angles of a spherical triangle are proportional to the sines of the opposite sides. And there is a little bit of a mystery. What do you mean by sine of a side? Now you remember the sine of the side is also an angle subtended by that arc at the center of the sphere. That's what I told you. So when you say sine, A also means length of this, it also means it's also the length of this arc which between B hat and C hat. A is also this angle that arc subtends at the center of the sphere. That's because I've taken a sphere of radius 1, right? So sine of A makes sense. A is not just a length, it's also an angle. See, the reason for taking a sphere of radius 1 is that all arc lengths become angles. They can be interpreted as angles. All plane arc lengths can be interpreted as angles. That's the advantage, all right? So you should not be surprising that, so in the plane case you get ABC, plane triangle. Spherical triangle you get sine A, sine B, sine C, okay? And what happens to the cosine rule? The cosine rule in the plane triangle, in the plane triangle case, you get cos alpha is equal to B squared plus C squared minus A squared by 2 BC. This is what you know, all right? It's also written as A squared is equal to B squared plus C squared minus 2 BC cos alpha. When writing it like this, it tells you that this is a defect with respect to the Pythagoras theorem. For example, if alpha is 90 degrees, then this term will go away and you will get A squared is equal to B squared plus C squared, right? That's your cosine rule. But then what happens to the cosine rule in the spherical case? It is cos alpha. So watch this. Oops. So watch this. You have to compare. You have to compare this with this. Okay. So in the plane triangle case, you get cos alpha is B squared is equal to B squared plus C squared minus A squared by 2 BC. All right. But here, what you get is cos alpha is cos A minus cos B cos C by sin B sin C. All right. And again, what you must understand is that it's not the side lengths A, B, C that are occurring, but they are trigonometric functions. So in the cosine rule, you get their cosines. In the numerator, you get the cosines, and denominator, you get sines. And again, remember, A, B, C are sides of the spherical triangle, but they are also angles. So it makes sense to talk about sine and cosine of those three numbers. Yeah, you can scale it. If radius is not 1, you'll have to scale it. That's all. That's not going to be a problem. You can write out, you can write out corresponding formulas, but it helps to look at it with radius 1. Okay. So the radius 1 allows you to treat the side of the triangle also as an angle equally, and in a way that's related to that side. Namely, it's the angle subtended at the center of the sphere by that side, right? That's the advantage of taking radius 1. Yeah. So now you have a question.
So these formulas will be applicable only for triangles in a sphere, right? Because
spherical triangle, yes, a spherical geodesic triangle.
Yes. So then, like for each curved surface, the formula will change.
For each
Curved surface, the formula will change.
Of course. Yeah, I mean, that's a very general question. In fact, even in the sphere, we are not done. See, even in the sphere, what am I doing? I am taking 3 points. I am joining them by these geodesics. Why should I join them by the geodesics? In the sphere also, I can wander and draw some amoeba-like thing, and say, now what about the trigonometry for that, right? I can go crazy. But the point is, yes, go crazy, but in a nice way, so that you don't end up crazy, but you come up with some crazy results which are really true, okay? So the idea is that you try to get inspiration from plane geometry. So what I want you to say is that the inspiration from plane geometry is that you have to look at geodesics. See, this is if you study differential geometry, one of the most important things is give me a curved surface. Give me 2 points on the curved surface. There must be many ways of going from this point to that point. What is the point? What is the path of shortest length? That is what a geodesic is. All right. And this is very, very important. For example, suppose you have a Mars rover or a land rover or some rover on the moon, and I want it to go from one point to another point. Okay, how do I steer it? How does it go? How does it go? Because it's going to operate on energy, and energy is limited. It's far, far away. So it has to optimize the energy. So it needs to find the shortest path to go. How do you tell it how to get the shortest path? What I can have is I can have something like LIDAR, to get the surface of that portion of the moon. And it will of course be very rugged, but I can make a smooth approximation of that. And then I can use mathematics to take these 2 points and plot a very close approximation to the geodesic. And then tell the then I know that if my rover goes by that path, that will be the shortest distance. That will conserve energy. You understand? So it has applications. But there's a lot of math here. You need to know, you need first of all the theory to get hold of geodesics on a curved surface, and then you need numerical approximations to that to be able to be computed in real time with data. Okay, so you see, this is going to be very interdisciplinary, right? But this is only the math part. In the math part, you always assume everything is nice, and then you first get a formula. And then the next stage is that, well, if it's not so nice, to what degree can you approximate that? So that you still get, in practice, you need only a certain level of accuracy, right? So if I am, for example, cutting a piece of wood, all right, maybe up to a millimeter, if I cut it to the right size, that's good enough for me. Of course, that's not going to do me, that's not going to be good if I'm going to fabricate a small chip, okay, where the components are only maybe micrometers apart. There I can't do it by hand, so laser etches it, because the laser is more precise and it's controlled by computer, right? So the point is, the degree of approximation depends on the application, but it can be achieved. But the point is, at the base of it, you need to know the theory behind it, right? So this is also very important in for example, in space science. See, suppose there's a you should have recently seen this slingshot thing, a kind of thing that they did, I think, where you have a planet, let's say the moon or Mars or something like that. I think they did it with the moon, if I'm not mistaken. So you see, you send a craft, okay, and then the point is that the craft uses the gravitation of the planet to swing around it for free and comes out. Okay, it's like if you're running in one direction and you want to turn, if there is a pole somewhere, you can just hold on to the pole, and you will swing you will turn around like this, and then you have reversed your direction. So this is a slingshot. So if you've seen this movie called Interstellar, okay, then you see there is this idea that they want to use a slingshot to, I think, go across something crazy, probably a black hole, I don't know. But I mean, imagination can go crazy, but science will help to achieve it at some point, hopefully. But the point is the following. The point is that what is happening there. I'll tell you what is happening, what is important. Differential geometry is working there. Because what happens, this is exactly what is Einstein's relativity theory. What gravity does is it changes the curvature of space-time. It makes flat space curved. That is why, for example, if you have a very heavy object like a a black hole or something like that, or a huge galaxy, objects which are behind that, their images you are able to see. This is what is called as gravitational lensing. There is a galaxy in front of you, there's a galaxy behind you, and this galaxy is out of your line of sight. But light from that, it bends like this and comes to you. Why does the light bend? Light never bends. To quote Einstein, if I'm not wrong, all motion is straight and all space is curved. Okay. So what is happening is that light is traveling in a straight line. The problem is that for light, for the photon, it is a straight line. It is a geodesic. But for space-time, it's not a straight line. It's curved, because the heavy thing in between has distorted the space-time. It has created a curvature. So if you study relativity, you will see that the curvature term is exactly due to gravity. Okay. So what you must understand is, even in space missions, the curvature is affected by heavy objects. Okay. So the moral of the story is that when there are massive objects, if you have no objects in space and you draw a grid, it will be like a flat grid, like a regular grid. But the moment you put something heavy, at that point, the grid will distort. The number of field lines will change. The gravitational field will, because of the high gravity, the curvature changes. And this is called curvature of space-time. All right. Because there's time is involved, because you can see it only if you move. You can see the change only when you move. All right. So moral of the story is that differential geometry is also very, very important. You look out at the sky, you just see, it looks flat, but then you realize it's actually 3-dimensional, but no, it's actually 4-dimensional. Lights that the stars and at least planets nearby, it's not very significant, but lights from the stars are coming from thousands of years ago, and all the images from Hubble and so on, they are from distant galaxies, which the light had left those galaxies millions of years ago. So what you are seeing is, actually you're seeing 3-dimensional space-time. You're looking at things as they are, but the point is each one has a time difference. It's actually you're looking at space-time. And the point is that this space-time is curved due to massive objects, nearby massive objects, and that's due to gravity. So the moral of the story is differential geometry is important in that sense. So you see these things, these ideas of trying to, understand what happens to, geodesics on something that's curved space. That's a very, very fundamental thing. It has applications to ordinary geometry and also to space-time and relativity and cosmology. All right. So differential geometry is such an important subject. Okay. So anyway, so let me get back. So you see, I also explained to you that this cosine rule and the sine rule, they become the ordinary sine rule and the ordinary cosine rule when you make the sides of the triangle very, very small. Then you use this approximation that as theta tends to 0, sine theta tends to theta, and cos theta tends to 1 minus theta squared by 2. If you do that, you get your usual sine rule and cosine rule. All right. It's like saying that if say within this room, if 3 of us stand and join the points where we stand by straight line segments, that's a spherical triangle. Because we are so close that the great circle passing through 2 of us, the arc of the great circle passing through 2 of us, okay, is literally this line segment up to a very high degree of approximation. Because the angle that we will subtend at the center of the earth, okay, you can imagine what angle 2 of us, the arc joining the 2 of us is going to subtend at the center of the earth. And whether it will make a difference whether you took that arc which is slightly curved, you can't even see it, or whether you took really the straight line segment joining the 2 of us, it's not going to make any difference, because what is the radius of the earth? 6,400 kilometers. Yeah. So at a distance of 6,400 kilometers, how are we going to subtend any significant angle at a point? Nothing. Okay. So you must understand that, when three of us stand in the room and then verify your Pythagoras theorem, or you're doing your sine rule or your cosine rule, it's actually spherical trigonometry, but because of this, because of the scale of it, it's actually plane, but it's actually spherical. If you go to really to the last dot, right? But anyway, so the point is, okay, so I want to indicate how does one prove this? How does one prove these things? So again, it's very, very interesting. The basis for that is a very classical theorem due to Archimedes, okay, the good old geometer of antiquity. So that is this Archimedes theorem, okay. And what is this Archimedes theorem? So let me tell you something about that. So Keshav, I have 5 minutes. Huh? When is their lunch, by the way? I think we are already into the lunch. How long do they have? Okay. Oh, there's some other thing that's scheduled here. All right, okay. So I'll close down. So let me come back. What is the how do you prove this? How do you prove this? So I want to indicate. So I thought that I will outline at least one of the proofs, but given that there's some shortage of time, I'll tell you just the starting point of it, and then hope that you will endeavor to fill up the gaps. And especially this is for, I mean, that will be, for example, the task for the couple of students who are going to be in my project. I don't know whether they have been allotted. They are being allotted today. Okay, fine. So that's a compulsory homework for them, and as part of the project. And of course, I would also appreciate it to be taken as a nice homework by the rest of you. It's just fun. Okay, I mean, don't do anything with the aim that you're going to get a score for this, or you're going to get a degree. I mean, some scorecard or marks or something like that. Just see this whole program. Please enjoy it. Try to the way you should enjoy it is. I'll tell you what will spoil it is if you try to hold on to things that you don't understand, and that may be because of technicalities, and there are a lot of technicalities. Technicalities take time, but that should not prevent you from understanding heuristically what's going on. Okay, proving Newton's law of gravity or even empirically verifying it is different from believing it. Okay, so first of all you should believe, and then you can quantify. Okay, so enjoy the width of knowledge and things, and don't get bogged down by details. Wherever you can catch a detail, that's good. Okay, but you're not going to get you're not going to get any marks for this. The whole point is you should enjoy doing science. Okay, so here is the classical theorem that is actually going to prove it. It's a very beautiful theorem of Archimedes. It's the following. So let me draw the three-dimensional space, and if you want, this is x, this is y, this is the origin, and then this is z. And what I'm going to do is I'm going to take this. I'm going to draw a unit sphere here. Unit sphere centered at the origin. So let me see whether this works. So I do this. Nice. Okay. So this is one. This is one. This is one. And this is also one. Okay. Right. Then this is of course this is the intersection of the unit sphere centered at the origin, radius 1 with the xy plane. And then I'm going to, of course, I'll draw another circle which is going to be like this. Yes, not so good, but don't worry about this part. Okay. So this is your this is also 1. So these lengths are all 1. So this is the unit sphere. Now what you do is I'm going to cover, I'm going to take the unit cylinder, okay, with base this circle on the xy plane. So I'm going to draw this. So here it is. So let me draw this like this, and oops. Let's see if I can draw a straight line. Great. Then I draw one more. Right? And you know, at this level, I'm going to restrict the cylinder to height, 1 unit above and below, so it's going to be 2 units, right? That's the diameter of this, any of the diameters of the sphere, okay? So I'm going to draw this, so, right? Here is one, and again here, here's another, okay? So here's my, so you see this is my cylinder C, okay? And here is my sphere, okay? And here is this very nice thing. What you do is you take a patch of the patch of area on the sphere. So this is A sub S. This is the area on the sphere, all right? You take the area on the sphere, and what you do is you assume that, so you make this, if you want physically, you make this assumption that, you assume that there is a light source here along this, well, I think, yeah, I think rather I think maybe this is not the way I should look at it. I need the radial projection. So what do I want? I want to, yeah, so I want the following thing. It's not even radial. So I want to take the horizontal projection of this on the cylinder, okay? I am horizontally projecting it onto the cylinder. So in the sense that, for example, if you took the upper hemisphere and projected it on the cylinder, you will get this upper half of the cylinder. If you take the lower hemisphere and projected it onto the cylinder, you'll get the lower half of the sphere. So I want a projection in that sense, okay? Now so there is this mapping, this is a projection mapping. This projection mapping is going to go, so let me call it as P is equal to proj, and this is a projection from the sphere. So this map is from the sphere to the cylinder, okay? And here is the theorem of Archimedes. So I take this A sphere, a nice piece of the sphere. So you think of it as being bounded by a nice, if you want smooth curve, it's curved surface, all right? So this blue thing is a curved surface, okay? And its area is A subscript SPH, spherical area, okay? I'm just going to project it, and I will get this A cylindrical. So A cylindrical is this, okay? This is a cylindrical area, okay? So for example, if you take the upper hemisphere and project it, you will get the upper half of the cylinder. If you take the whole sphere and project it, you will get the whole cylinder. Of course, when I say cylinder, I only the restricted portion, okay? Height from -1 to +1, right? That is Z coordinate from -1 to +1. So what is the theorem? So this is the beautiful theorem of Archimedes. Archimedes is this A spherical is equal to A cylindrical. Okay. So Archimedes theorem is that this horizontal projection is equiareal. So that is a beautiful theorem. The horizontal projection is equiareal. That means it preserves areas. Okay. So for example, you can check if you take the full area of the sphere. What is the area of the sphere? It's 4 pi r squared, right? So r is 1, so it's 4 pi. So that's the area of the sphere. If I project it onto the cylinder, I'll get the whole cylinder. What is the area of the cylinder? The height is 2, right? And what is the circumference? Circumference is 2 pi. So it's 2 pi into 2, it's 4 pi. So the full area of the sphere projects to the full area of the cylinder. Take a hemisphere. If you take a hemisphere, then its area will be 2 pi, half the area of the sphere. You project it to the cylinder, half the cylinder. It's again 2 pi times 1, so 2 pi again. Two simple illustrations. So this is an equiareal projection. Okay. So this is the beautiful theorem of Archimedes, and the point is, what is an exercise? You can prove this theorem by using calculus, and you will have to use multivariable calculus. You have to use 2-variable calculus. Because the point is that you have to compute this blue curved surface area, all right, and you need to use multivariable calculus. So one exercise is to prove this formula, and don't be scared about multivariable calculus. It's as easy as 1-variable calculus. You have to use partial derivatives instead of total derivatives, and the rules for partial derivatives are just like the rules for usual derivatives, except that you keep only that variable that you're differentiating with, and all the other variables are thought of as constants, right? It's not a big deal. You can learn it. So if you use multivariable calculus, you can prove this. This is Archimedes theorem. Now, what is the beauty of this Archimedes theorem? So here is a nice takeaway, and I think I'm also ending. I'm nearing the end of my talk, and also I've exhausted the time that was given to me. Here is a beautiful thing. So suppose I take a point, for example, this is the North Pole and this is the South Pole, if you want. And suppose I take, what is called a loon. Okay, I mean, it's called a loon because it looks like, if you want, a face of the moon, if you want. But what I mean by that is, see, basically what you do is you take this plane here. Okay, mind you, this is passing through the center of the sphere, and then there's another plane which is for the other side. Okay, do you see that there is a blue plane which is actually a half disk, and then there's this green plane which is intersecting in half a disk. These are two planes. In fact, I can extend them backwards also, right? And here is the important thing. There is this angle here, this angle, which is the angle between these two planes. And if you call this angle as theta, okay, then here is the interesting thing. The area of the loon is the curved part on the sphere. It will be 2 theta. Why is it 2 theta? Project that loon onto the cylinder, okay, and what you will get is that on the cylinder you're going to get a, literally, if you fold it out, it's a rectangle, all right, and this length is 2, okay, and this length is theta, because that is the angle subtended at the center. Radius is 1. So the area of this rectangle is 2 theta. And why is this true? This is because of Archimedes theorem. Because if I take that loon and project it on the cylinder, I'll get a patch. I'll get a vertical patch which I can fold out to be a rectangle. So the area of this loon is 2 theta. Okay. And now I don't have time, but you can do this. You take now a spherical triangle, okay, and a spherical triangle can now be made out of 3 overlapping loons, okay, and then you can use this formula for area of a loon and prove all that you want. You can get all the spherical trigonometry from that. You can get the cosine rule, you can get the sine rule, and so for example, if I have these two, then I'll have, if you want, the diametrically opposite points, which are called antipodal points, Okay. And what will happen is that, I'll have, if you draw loons like this, it will go like this. Okay. And then there's going to be this, oops. This is a short table. And then there's one here. So, if this is your A hat, B hat, C hat, then you have on the other side, you have I will call this as A prime hat, B prime hat, and C prime hat. Okay. And you'll get this other triangle on this side. Okay. And what you must understand is that there are these loons that come into the picture. Okay. And for example, if you picture it, you see from C hat through B and then all the way goes like this. You see there is, and then from A hat, if I take like this, if you think about it, there's going to be a. So I have to draw this carefully. All right. Let me not attempt to draw it now with time being a constraint. So what I want you to understand is that you can think of a spherical triangle the following way. Take two of those points on an equator and take the third point and then start drawing loons and use this fact that the area of a loon is 2 theta, and you'll get something very amazing. You'll get the following. You'll get two things. The sum of the three angles of the triangle will be greater than 180. The sum of the three angles of a spherical triangle will always be greater than 180. What is the difference? And that is a magical answer. It is the area of that triangle. I'll just put A. Okay. So this can be proved using this formula for a loon that you get from Archimedes' theorem. And the beautiful thing is that it confirms you draw any spherical triangle, the sum of three angles is greater than 180. And why is it greater? The difference is exactly the area, the curved surface area of that spherical triangle. Okay. So when I say area here, it means curved surface area. Okay. So you get a very beautiful result, right? And there's another important result that I want to tell you. So this is what is striking about spherical trigonometry. You can derive all those sine rule, cosine rule, etc. Okay. Here's another interesting thing. In spherical trigonometry, similarity is the same as congruence. So this is another surprise. Okay. This is another great surprise. There is no difference between similarity and congruence. Okay, you get these two amazing results. Okay. If anybody has any quick questions, I can take a couple of them. Otherwise, we can call it a day. Yes. They are the same, right? I'm not. When I say cylinder, I'm not including the top and it's the open cylinder. It's only the curved part. I'm not taking the plane, which are like the lids of that cylindrical, if you want, box. It's just 2 pi RH. I'm not taking the disc above and below. I'm not taking that. I'm only worried about the horizontal projection that projects only onto the sides of the cylinder and not onto the top. Okay. Yeah. So if there are no more questions, I think we can call it a day, and we can.
On behalf of the entire RSIC team, I'd like to thank Professor T.V. Balaji for enlightening us on the types of curves, the applications of the curves and the approximations, and how differential geometry is applied in physics and all that, and also for introducing us to the proof of spherical trigonometry. So thank you, sir.